Let's go ahead and solve this one. We have air. It's contained in a piston cylinder assembly, and it's initially at this temperature, pressure, and volume. So 25 C, 1 bar, 1 liter. It is rapidly compressed so that there is negligible heat transfer. We could say that it's adiabatic compression. There's no heat transfer. During the compression, the pressure-volume relationship is PV to the 1.4, so it's a polytropic with N equal to 1.4, PV to the N equal to a constant. The final volume is 1/10 of a liter. Assume the ideal gas behavior for the air with constant specific heats of C sub P and C sub V, and the ratio of C sub P over C sub V is also given 1.4. Okay. Determine the final pressure in bar, the final temperature in degrees C, and the work from the perspective of the system being the air, in kilojoules. Okay. So the final pressure. Well, they're given the polytropic process, so we have that the pressure at state 1, the volume at state 1 to the 1.4 is equal to the pressure at state 2, volume at state 2 to the 1.4. So if we're interested in solving for the final pressure, it's the initial pressure, the initial volume over the final volume to the 1.4, substitute numbers. We have 1 bar, and then we're going to have V2 over V1. V2 is 0.1. The liters are going to cancel. Divided by 1.0 to the 1.4. And when you run the number, P2 comes in at 25.12 bar. So that's the answer for part A. Very good. Okay. The final temperature in degrees C. Well, even though it's being compressed rapidly, and the pressure-volume relationship is described by this polytropic equation or polytropic process, it doesn't mean that it stops behaving as an ideal gas. Air still, even though it's being compressed rapidly like this, behaves as an ideal gas. So the ideal gas equation is true. So P1V1 divided by T1 is equal to P2V2 divided by T2. It's still an ideal gas. At the beginning, at every state in between, from the initial state to the final state, every intermediate state in the process, as well as at the final state. So if we're interested in the final temperature, T2, it's equal to the initial temperature T1 times P2 over P1 times, it's at V2 over V1. So we have to say, well, what is our temperature? Now, a lot of students will just put 25 degrees C here, but why would that be wrong? Well, the ideal gas equation, PV is equal to NR bar T, requires the absolute temperature as well as the absolute pressure. So it's an error to put in temperature in degrees C, that's relative scale, and it would be an error to put in pressure and gauge pressure. It has to be absolute pressure. All right, so we correct it by adding 273.15. That makes the temperature in Kelvin. Our two pressures we just solved for, 25.12, started at 1 bar. And then our volume, our final volume is 1/10 of a liter, and it starts at 1 liter. And so when we run our numbers, T2 comes in Kelvin to be 748.9 Kelvin, and we convert that to degrees C by subtracting 273.15, and we find 2 in degrees C comes in at 475.8 degrees C. Done. All right. Now, the last part, we want to calculate the work for the process. We'll write down the first law for the process from initial state 1 to 2. I often just write it as EB. What's the energy balance? Well, the equation is that you have the mass times the change in the specific internal energy. We're neglecting changes in kinetic and potential energy, so that's the only change in energy of the system, is equal to the heat added to the system during the process and the work done by the system out. Well, it's a negligible heat transfer. It's stated up here, negligible heat transfer. We would say that's adiabatic, no heat transfer. So the work 1 to 2 is equal to the mass times the U1 minus U2. Okay, a little bit of work. How do I find the mass? Well, we'll use the ideal gas equation. The mass would be the initial pressure, initial volume, divided by the gas constant for air times the initial temperature in Kelvin. Okay, I think we can do that correctly. The R for the air is the 8.314 R bar divided by 28.97 for the molar mass of the air. Boom, you get that, plug it in, and you can calculate the mass of the air comes in at 0.00, well, that's a bad looking bunch of zeros, 0.00117 kilograms, and you would keep more digits in your calculator. All right, now we struggle with what is the U1 minus the U2. Well, for an ideal gas, there's three things that you remember. PV is equal to N R bar T, that's one thing, but also U is a function of temperature only, and enthalpy is a function of temperature only. Those three things make up our ideal gas model. So U is a function of temperature only. Also, we have the relationship that, and I'm just going to continue the discussion up here, du dt is defined as, here, let me write it this way. We've defined C sub V as the rate of change of internal energy with respect to temperature holding volume constant. And if U is only a function of temperature for an ideal gas, it is. So we'll say, and this equation now changes for an ideal gas from a partial derivative to an ordinary derivative holding volume constant, so that we have that the change in U is equal to C sub V dt. Now, there's a little subtlety here in the sense that if U is a function of temperature only, do I really even need to consider from the calculus that the second variable V has to be held constant? If U is not a function of V, then that drops, and it's just truly an ordinary derivative. U is only a function of T only. And this is a real subtle point, and a lot of people will miss that point in the calculus and in the math. But this is a result. They'll say, oh yeah, I accept that. And then what you have is you'll have the U2 minus U1, if you have constant specific heat, to just C sub V times T2 minus T1. And so applying it down here, we have that the work 1 to 2 is the mass that we calculated, the specific heat constant volume, and then T1 minus T2. All right, so we'll substitute our numbers. They give us, well, we calculated the mass. I'm running out of room, so I'm just going to say here's the mass down here. The C sub V is right here in the problem statement. And we calculate the temperature, inlet temperature is given. We convert it to Kelvin, just like we have the outlet temperature in Kelvin, or do the difference in degrees C. And when you do this, the work 1 to 2 comes out to be negative 0.3783 kilojoules. And we'll box it and call it done. Now, what we're going to do is we're going to plot this process on a PV diagram. So this is a pressure volume diagram. We start at a large volume, 1 liter. We go to a small volume, 0.10, or 0.1, 1/10 of a liter. And we start at this pressure, and that's the polytropic process. It has some curvature going up like that. And this is a compression process. So a lot of times when students are struggling with this, they'll say, okay, I follow the math, but you've made an error, and the error has to be somewhere in here because, quite frankly, this process volume is not a constant during the process. That's a bad looking volume, but let me try and redraw that. They'll say the volume is definitely not a constant, or the specific volume is definitely not a constant during this process. Hence, you've come up here and you've used this C sub V. It's not. You can't do that. You can't calculate delta U is equal to C sub V dt because this C sub V, what's that V mean? That's the specific heat constant volume. But when you have an ideal gas, and an ideal gas is a function of temperature only, you can drop this holding the volume constant, just like I described right there, because U is a function of temperature only. The partial derivative in the definition of C sub V turns into an ordinary derivative, and you can just unravel it, just like I've shown. And so I hate to say it, but a lot of students will struggle with this. People in the internet will struggle with this. People leave bad comments on your YouTube video going, oh, you don't know what you're talking about. But this is still correct. This is true because it's an ideal gas. Yes, we use C sub V right here in calculating the change in U. It's C sub V delta T for constant. Remember, this is constant specific heats. I'm not using the air tables at all. Just assuming constant specific heats. And there it is. I tried to explain what some people will find as a stumbling block and will give them a hard time as they're learning thermodynamics. But there it is in the mathematics. When U is a function of temperature only, the partial derivative turns into an ordinary derivative, and it's a lot easier on the math. Well, there's one more point that I'd like to make. And that is, some people would say, well, why did you even use the energy balance? Why didn't you go and calculate the work 1 to 2 from the integral P dV and put the mass in there right there? But you have the pressure volume relationship, and you can do that integral, and we've done that integral. Let me expand this to a new, all right, let me scoot down. And that's definitely true. And that equation, you can find it in our textbook. I think it's like equation 357. Yeah, equation 357, where they've done that integral for a polytropic process. So the integral P dV is equal to, here I'm going to put the way they've written it is the mass, R for the gas. Then they have 1 minus n for that exponent in the polytropic process, 1 minus n. And then they have the T2 minus T1. Okay, that's for an ideal gas with n not equal to 1. Well, in this case, n is equal to k, which is 1.4. Okay, so if we want to manipulate this equation, we'll put our mass, our R, and instead of 1 minus k, we'll put k minus 1, and then we'll switch from T1 to T2. And so that's our work, 1 to 2. And then we look and we say, uh-oh, we've seen this. That's simply C sub V. And so it does go in circles. The work 1 to 2 is C sub M, C sub V, T1 minus T2. That's just what we were using. Here, they got it from the integral P dV, from work from first principles, or same result from the energy balance. So it's not that one method is completely different than the other method. They're consistent. I mean, but again, a lot of people will look at this equation and say, you've got an error. Somehow there's an error here. That specific heat is constant volume. That's what that V means on the C. But the problem is definitely the gas is being compressed. The air is being compressed, and V is not constant. It's changing, going down. All right, with that, I'm going to go ahead and stop.